My name is Angad, and I'm a performance engineer at Causal. You can think of Causal as a 1000x spreadsheet. So it's 1000x because it's really, really huge. It's used by finance teams across the world to build really large FP&A models, revenue forecasts, headcounting models, and stuff like that. And I'm going to talk to you today about the performance engineering journey that we've had with Causal over the last year and a half or so, and scaling this spreadsheet engine from 50,000 cells to 150 million cells. And this is primarily my life's work for the last year and a half or so. And I hope you're as excited about this as I've been. To give you a feel of the product first, because I think a lot of yes, to give you a quick run through of the actual product so that you understand some of the performance constraints that we deal with and sort of appreciate the rest of the journey. So the way this works is that Causal is a spreadsheeting tool, and here we're building a business model for a mobile app, right? Let's say you're pricing this premium app at $5 per install, and you've got a user growth rate of 5% to 10%. And Causal is pretty good at handling uncertainty intervals like this. Now I simply say, users are equal to previous 1 plus the growth rate, right? And that'll give me a nice time series of data through all the months, as soon as I feed the seed numbers there. Here I'm segmenting users with another category called platform. So I can now break down this time series into two more. So I've got iOS and Android. And revenue here now becomes very simply price times users, right? So far so good. And what Causal will do now is intelligently infer that revenue also has to be broken down by iOS and Android, right? I can quickly visualize that by dragging and dropping the revenue variable on the chart. And let's say now I want to break down my platform revenue by region. So I want to look at user installs by, say, US, UK, and EU. I can go ahead and add the region category. And as soon as I change the formula for one of these regions, you'll see that revenue also updates to have that second category. Right? And some of you have probably already spotted the core performance constraint scaling a spreadsheet like this, right? Which is that every additional category that you add adds an entirely new dimension of cells to the spreadsheet. So categories exponentially blow out the size of a spreadsheet at Causal, right? And this is a very straightforward calculation of how you can very easily come up with, say, 1 million cells in a spreadsheet. And most businesses typically use a lot more than 10 variables to express their business models, right? So you're talking about spreadsheets which are tens of millions of cells optimistically, and sometimes even hundreds of millions of cells. And this is exacerbated even more by the rate of growth that Causal's seen in the last year and a half or two that I've been around for. And every year we have to come up with orders of magnitude of performance to sort of support the newer use cases that customers find along the way. And this is really the journey that I'm going to take you guys through. So we started with 10,000 cells, and that was a system that we would support in the browser itself, right? We moved that to Node.js, and with Node.js we basically moved the compute from the front end. So in the front end you have formulas, you have compute happening in the browser. Node.js would just be doing that same JavaScript stuff with a dedicated server in the cloud, right? And then for multiple reasons, we decided to move to Golang. I'm not going to dive too deep into those, but essentially we found that Go was just a much better fit for handling things that were inherently parallel in nature. And this was really my email to the CTO at Causal. You can see clearly that I've relied on Golang quite heavily for my career here. But my pitch was, if I just simply port the evaluation engine to Go line by line, you're probably going to see somewhere close to a 5 to 10x speed up, right? And we released the first version of the evaluator in Go. We call it cow, again, for reasons I will not delve into, but it's very nice to have an emoji for your microservice. Once we shipped this, we were up to about 500,000 cells, right? 500,000 cells, not a bad improvement, but this was now time to sort of get in there and really start optimizing stuff. And we did what most people do here, which is use simple sampling-based profilers, right? So we would use something like GoTool bprof, and the profiler essentially captures the runtime stack and tells you how much cycles you're spending, how many cycles you're spending on like what functions, and then you jump in there and you fix that stuff. The learnings we had from sampling-based profiling on our application were quite straightforward. Mostly you'll see they're around allocation here, right? So make sure that you sort of reallocate enough space for your slices. If you're using string buffers, make sure that they've got enough space in there. They're not regrowing every time you do some sort of mutation. And use sync pools to sort of reuse your old allocations. Make sure that you're relieving pressure on the garbage collector where you can, because it's just marking and sweeping much lesser stuff with every iteration done, right? And the more interesting, I would say, funkier sort of profiling that we did was one of the limitations we ran into with sampling profiling is, essentially in a concurrent environment, sometimes it's non-intuitive what gives you the highest sort of ROI of optimization. So sometimes you look at a function that's only, say, a second or 2 seconds of your profiles, but then you actually speed that up and your overall runtime increases by, say, 5 seconds or 10 seconds. And the real reason this happens is because of multiple coroutines and contention between these threads, right? So we came across this pretty interesting tool called Causal profiling. It's no connection with the company. It's this binary that ships called cause. And what this does, it says, if I could hypothetically speed up like one part of the software at a time and figure out the total runtime improvement, I know what's like the highest ROI optimization to make. And obviously, since profilers can't magically speed up parts of your program, what cause does is it sort of slows down everything else, right? So it picks a control. So it would control like, say, F or G at a time. It'll slow up all other functions, and it'll tell you, hey, if you speed this up by 20%, looks like overall runtime improves by, say, 35% or whatever, right? So a pretty interesting tool that we used to get, I would say, still a couple more incremental gains. And finally, we came up with a lot of patterns to sort of help us build concurrent code quite quickly. So, the first one's quite no-brainer, right? Like probably what they teach you in engineering school. Avoid semaphores where you can. If you want, if something can be read concurrently, just sort of initialize it up front, and then you're done. You don't pay that log cost again. We sort of shied away from channels. The performance model that we found for channels was akin to an array with a semaphore on it, primarily because you pay that penalty for the first in, first out property of sort of using a channel, right? So the parallelization model we used was like take a bunch of work, have a error group, section of that work into the error group, and then just basically wait for it to execute. The way we would sort of spin out those coroutines out of the error group was by creating our own context. And this context structure you'll see is wrapped around the standard Go context, right? So this would give us the nice like deadlines and cancellations and stuff like that. But at the same time, I've moved the ownership of all the reusable allocations and pretty much all the memory allocations that the Go routine wants to use into the context. So now I have this free sort of isolation of memory between the different Go routines that are running. I don't have to worry too much about race conditions between them, right? Finally, we just run go test race in CI. If you take a big enough workload and just run go test race, it's actually really good at figuring out exactly where code will potentially race. But of course, the caveat there is that it depends on choosing the right workload and making sure your CI is running on more than one thread, right? And then our profiles were looking sort of like this. The stuff that looked the scariest was malloc GC and GC write barrier and stuff like that. So we started looking at heap escapes, right? Fun topic. I'm not going to dive too much into the details of Go's garbage collection today, but I would highly recommend you check out GopherCon 2018's Allocator Wrestling. Fantastic talk on the internals of the GC itself. But I want to take you through this snippet of code to sort of help you understand the value of doing some heap escape, right? Some heap escape analysis. So if you look at these two functions, the only thing that's different between them is the fact that the first one has a dead if condition, right? So it does ARR PTR at I, and it takes the pointer of value. But that branch is never going to execute, right? Because value is never going to be equal to value plus 1, right? For all iterations, fundamentally this code should be executing the exact same operation, which is ARR at I is equal to value. However, when you compile this code, the compiler does not see that the first branch is never going to execute. So what it does is it actually heap escapes value. So you have one heap allocation for every iteration of the loop. And when you run the benchmark, you'll see here that it's almost 5 times slower, the first version, even though fundamentally doing the exact same operation underneath. Now, this is obviously a synthetic benchmark, right? But we found very similar patterns to this, where we sort of had to do a bit of branch prediction ourselves and reduce the sort of overall escapes that the code was doing. And we found some pretty interesting gains with with sort of patterns like this. Finally, the sort of 3 rules of thumb we now use to review code is, if you're using pointers, they're typically pointing to something on the heap. So that's a good indication that something that you're using the hot path is escaped to the heap, right? The second is interface method calls. So if you say something like func.println and pass any argument in there, because of the way Go works, because of the fact that at compile time it doesn't know if it needs to allocate those interfaces to the heap or not, pretty much every argument that you pass to these functions will escape the heap. Finally, you've got unknown length allocations. So if you've got a slice that you don't know at compile time how big it's going to be, that slice is going to get thrown onto the heap again. And sometimes you can probably use like some optimistic size up front and make sure that the compiler is putting that stack for you, putting that sort of array for you on the stack, right? So all of this stuff got us to about 2 million cells, which was fantastic, right? Like we started with 50K and we're up to 2 mil, and it's good going. But the problem we realized we're going to run into very soon is, what's next? Like how do you sort of figure out if there's a faster paradigm that you can build your software, right? And the realization we start to have at this point is that profilers are great when you've got a mental model of your application, you've got a profile, and the profile and the mental model don't match, right? The problem starts is when the profiler's profile and your mental model are in complete alignment. So if the profiler and the mental model don't align, and you see things on the profile like logging or network access, and you can basically optimize them out. But if they align, the bottleneck is now your mental model, not your engineering effort, not the profile itself. So as a result, we decided to establish some sort of performance baseline to tell us what's the absolute fast any application can do the workloads that we're considering. And we were very lucky on our journey to meet Simon at the time. Simon at the time had just left Shopify. He served there as a director of engineering for a while. And Simon has this philosophy of napkin math, where I think that the best way to explain napkin math is the story Simon tells, which is when Elon Musk was building SpaceX, he went with the amount of metal that you need to build a rocket, and he multiplied that with the spot prices of said metals on some metal exchange that he found, and he said, okay, this is the X dollars that you need to build like the world's cheapest rocket, right? And if the retail price of a rocket is 1,000, 2,000 times that, then that's the area of innovation or optimization that my company is going to do. And this translates quite cleanly to software, because typically software is bound either by CPU, memory, or I/O, right? And Simon's actually got this table of cost that he encourages you to memorize that helps you build these strong napkin models in your head and allow you to sort of build these performance baselines very, very quickly. I highly recommend you check out his blog, which I've linked to on the slide. And my favorite quote from Simon is this, is that, if you want orders of magnitude performance increase, you've got to leave the profiler behind and start looking at, first principle thinking. So the napkin model Simon came up with, this is quite straightforward. You've got 8 bytes for a 64-bit float. 1 billion cells means one variable would take, say, 8 gigs. And if I'm adding, 2 variables, which is a plus b is equal to c in my spreadsheet, that's 3 variables. So I've got about 24 gigs of memory. And the throughput I can establish there is, I can say, hey, I should be doing, 1 gig every 30 ms. And my baseline, therefore, is 700 ms, like theoretical, absolute fast limit. Obviously, our application was very, very far from this, right? But that's an indication that we were doing something horribly wrong. So we start talking about the basic data structure in which we represented the entire spreadsheet, right? And at the time, as dumb as this now sounds, I represented the entire spreadsheet as a hash map, right? And at some thought process here, my first argument was, hey, most of the cells are empty, so why do I take that allocation cost up front? In a hash map, I don't have to worry about it versus an array at sort of having a big chunk allocated, right? The second argument I made was, in none of my profiles would any of this hashing stuff show up. So like I wasn't really paying necessarily a lot of cycles to hash this stuff, right? And until it showed up on my profile, why would I waste my time refactoring my entire code base? And Simon's point to this was quite simple. He says, more importantly, the cost of a hash map would never show up on profiles because the cost of a hash map was random memory access, right? And what he said was that what I was paying for with my hash map was the fact that my CPU would never find the memory I wanted in cache, almost never. And that was the reason my application was orders of magnitude slow. And this was a lot of information for me to take. This is a very different way of looking at my code. And the way I could sort of build a very simple mental model of CPU caches for you is, a CPU cache is trying to remember the memory addresses that you've accessed so that they're much faster to reach when they need them for future instructions, right? So the temporal locality of a CPU cache, which is stuff that I've accessed most often, is asserted by the LRU eviction policy, right? The spatial locality of the cache is basically by looking ahead in adjacent memory. So if I'm accessing the first element of an array, for instance, right, the CPU knows I'm probably going to access like the second, third, and fourth. So it's just going to prefetch that stuff, and I'm going to find it in my cache when I hit those indexes. And lastly, this is a bit of a technical detail, but on most modern computers, what it is prefetching is about 64 bytes of data. Now, when I saw this schematic, I mean, this was when it sort of dawned upon me that we were looking at orders of magnitude of performance improvements, right? Is if you look at the difference between L1 and main memory, that's 80x in latency, right? Give and take depending on CPU architectures, but it's a massive difference. It's not percentage basis anymore. And this is essentially why CPUs love processing arrays, right? And I would say this is a fundamental rethink of how we write code, because so far we've been told we can just sit on our butts and hope to God that CPUs get faster year on year, and we don't have to worry so much about optimizing the hell out of every single assembly instruction that we're running, right? But turns out memory access, if that starts becoming a bottleneck for you, you're looking at newer chipsets which are doubling in throughput but also increasing in latency. So if you're not exploiting this spatial locality of data in the cache, you're actually getting slower with these newer chipsets that are rolling out in the market. And this is very, very, I think, non-intuitive for someone who's lived in the law of Moore's law land for a very long time. So to sort of prove that this was, these are some basic gains we could book by making these changes, and it was quite a big refactor to think about at the time. We wanted something that we could run on our laptops, right? Keep it fast and snappy and come up with some quick numbers. Two, we also realized that if you run this on cloud, given the layers of virtualization there, you're going to start to see quite a bit of variance, quite a bit of, because ultimately this is very low-level optimization you're looking at, right? And finally, we thought the best way to approach this is by creating a synthetic benchmark, which is sort of taking the causal engine and what it's trying to do and reducing it to a very simple program that we can reason about very easily. And this is what we came up with, right? You can see the difference in the two. There's more than one. So first off, the way we've defined the cell structure, which is cell 88, right? Cell 88 has a padding of 80 bytes to sort of mimic what the structure we were using in production, right? And this is important because the size of the structure is going to impact how much stuff I load in my cache line, right? I'm also going in and moving my map to the array, which is probably the main meat of this benchmark. And the other change you'll notice there is I'm going from a map of pointers to cell 88 to a map of struct, right? So I'm also removing one additional indirection of memory. So this sort of gave me a speed boost of, I would say, from 6 seconds to 400 ms. And this was, again, massive orders of magnitude. Very promising improvements. And these were the sort of learnings along the way. I'm going to, in the interest of time, skip through some of this, but essential learnings, smaller structs. So we went from arrays of structs to smaller primitive arrays so that we have information density in the cache. If you're using arrays, you can use indexes. Indexes are smaller as integers instead of using 64-bit pointers. So pass around indexes don't pass around pointers. And finally, your API starts to evolve to reflect what the CPU is doing a little bit more than what the API looks for a human reader, right? And then we finally got to about 150 million cells. That's where we are right now. And we're hoping by this time next year, we can probably, who knows, double that. The roadmap for Causal, I'll get to in a bit. The first sort of interesting note on the hardware side, I would say, is we just flipped a switch to go from 30 to 50% fast on the cloud. this, well, the best reason I could come up with for this is because between Cascade Lake and Ice Lake, the L1 cache size increases. But given that I'm not a CPU architecture expert, all I can tell you here is I have no clue. I would just highly recommend you go into your cloud providers and change those settings and mess around a little bit, see what works for your own workload. These things change very dramatically even within the same generation, right? And this is the roadmap as promised. We've got some very standard stuff. I think the more interesting stuff would be the hardware acceleration bits. But if any of this stuff interests you, please reach out to us at causal.app/careers, and that's my Twitter. Do we have time for questions? All right. Well, thank you.